Hello everyone, it's Tuana. Today, with my teammates Kemal and Pınar, we will present our mechanical engineering design project, the Rope Crawler. Our objective was to design an autonomous rope climbing robot for transportation and inspection in challenging areas where traditional vehicles cannot go. As you can see, we successfully manufactured the prototype that travels along a horizontal line without any deviation. We focused on mechanical stability, high torque performance, and real-time wireless control. Here is our initial design. We choose our materials based on a strong strength-to-weight ratio, 3D printed PETG for arms, and laser-cut acrylic for chassis, connecting links and gears. While we kept these exact materials in our final robot, the physical arm geometry and the linkage mechanism changed. During our initial structural FEA simulations, this arm design showed no signs of mechanical failure. However, when we manufactured the physical prototype and mounted the motor and the electronics, the actual center of gravity shifted unexpectedly. Why? Because electronic components were modeled as simplified point masses in CAD, but in real world, the complex mass distribution of the actual electronics created secondary moments that only became obvious during dynamic testing. This taught us the critical difference between the ideal simulation environments and the real-world assembly tolerances. So, this shift caused a critical alignment issue whenever the robot tried to lift its arm forward onto the line. To resolve this imbalance, we modified the arm geometry and the linkage mechanism. Now Pınar will continue. Hmm. To verify our design, we performed a static analysis for horizontal climbing equilibrium. We modeled four forces: a weight, the vertical tension from the linkages, the driving force from the motor, and the opposing friction. Using Newton's first law, we calculated that our powertrain must provide enough torque to satisfy the occasion driving force minus friction force equal to 0. This was the baseline for our motor selection. And this is a motion analysis. We use ANSYS to simulate the structural integrity of our PETG arms. In case 1, 20 Newton load, we simulated a worst case scenario where the entire robot weight is supposed by a single arm. The maximum stress was only 3.3 MPa, giving us a very high safety factor of 15. And in case 2, 10 Newton load, under normal load sharing, the safety factor increases to 30. The maximum deformation in both cases was under 1 millimeter, confirming that our arms are extremely stable and safe. And
In this slide, we have our electrical architecture. We first start with our not actual 12 but 11.1 volt battery. It then goes to buck converter, then our brain of the system Arduino Uno R4 Wi-Fi. We have chosen Arduino Uno R4 because of its Wi-Fi capabilities and that we can control it wirelessly. Next to our electrical architecture, you can see the how we can control our system. We control it by just using the IP address we get from the Arduino's app, and we use it to move it forward, backward, stop it, or to tell it how much it should go as in limits. But even when you set a limit, we have ultrasonic sensors that will detect when there is something on the way And when it detects it, it will stop automatically, so there is no need for doing it manually. Then we have our motors. Uh, our biggest hardship in this project was to find the perfect motor. In our torque analysis, we had problems with in our torque analysis because the 30 RPM 12 volt motor was not enough. And even though it was very like not enough, we also used an very low driver, not something for heavy duty, and it also cut power of the motor. It had 2 or 3 volts just for the motor driver. So as our solution, we have used again 12 volt, but 5 RPM motors. As the voltage is the same, however, the RPM is 6 times less. It has 6 times higher torque. And so to use all 12 volts of this, we have used a motor driver that is a heavy duty. So that's how we finally managed to do it.